Good evening, ladies and gentlemen, and welcome to Quest. As usual, we have two teams with us here tonight. On my right is the SN Bose team from various schools in Calcutta, schools and colleges. And on my left-hand side is the Albert Einstein team. Now, you would recall that last time we showed you an experiment with a hot iron, and we will play it back to you now. Now this iron is really cold. Now you can test whether it is cold. Right? It's cold. Now you all know that if I try to iron a cold iron, really nothing happens. Okay? It doesn't get pressed at all. However, if I use a hot iron, then also it doesn't really work very much until and unless we sprinkle some water. So let me put some water. Okay? And then, as the fellows do on the streets, we do that, and then we start ironing. And as you all know, that this time, of course, it works. So now the question to the viewers is, why do you require a hot iron, number one? Why doesn't a cold iron work? And number two is, why do you need to sprinkle water on a starched piece of cloth before you can start, before the pressing becomes effective? Now, we received a lot of very interesting answers. Not all of them right, but some of them are right. The correct answer is this. Do you take a starched piece of cloth and then sprinkle water on it, then the water dissolves the starch and the cloth becomes softer and more flexible. Then when you press it with a hot iron, the water evaporates, leaving a flat starched surface behind. So that's the correct answer. And now before I go on to today's program, I would like to also tell you that last time we showed you an experiment with a kettle, and we showed that before a kettle, the water in the kettle starts boiling, there is a singing sound from the kettle which stops once the water actually starts boiling. Now the answer that I gave you was that the dissolved air in the water adjacent to the hot bottom expands and forms bubbles, and these bubbles rise through the water, and when they come into contact with the colder water above, they collapse, and that's how the sound is produced. Actually, there isn't too much of dissolved air in water. The main effect comes from in the following way. The water which is in contact with the hot metal surface below actually vaporizes first. So there are steam bubbles which are formed, and it's the collapse of these steam bubbles which produces the main sound. So I apologize to you for the slight wrong answer I gave you last time. Now we will begin today's program, and I'll be assisted by Mr. Priyobroto Basu. Mr. Basu. We have two candles here. They're more or less exactly the same except for their color. Now this candle has been burning for some time, but not this one. We will light this candle, and please notice how long it takes, roughly. This is a question for the SN Bose team. So you see, it took a little bit of time for it to light up. Now I will extinguish this one and hold the lighted candle near it. Again, notice how long it takes for it to light up. See, it's almost instantaneous. I'll do it once more.
Sorry? Shall I do it once more? You see, this time it lights up almost instantaneously like a gas cooker. Now the question is, why is there this difference between the two cases? 40 seconds. Like to answer now? Yes, let's hear the answer.
In that the candle which was originally not burning, actually a candle burns when you apply the heat to the candle, the part of the wax melts, and that rises up by the capillary action over the wick, and it starts burning. So when the candle which was originally not burning, you applied that flame to it, it took some time for the wax to burn and to rise up by capillary action, and then it starts burning. But in this one, the one which was burning earlier, the wax was already melted, part of it. So as soon as you applied the flame, the wax immediately rose up and the candle starts burning.
Yes, it's quite a good answer, but there is a little bit that's not yet explained, because we didn't really have to take the lighted candle and touch it to the wick.
There is some the wick.
The wax vaporizes.
That's right. Yes, absolutely right. So that's the complete answer. So you get 10 marks for that. So I will explain the answer for the benefit of the viewers. What this brilliant boy said was this, that you see, when a candle burns for a while, then the wax melts, and not only does it creep up the wick, but it also forms a wax vapor, which is a hydrocarbon vapor. And when we bring anything lighted near such a vapor, it immediately catches fire. Right? Thank you. Now, Mr. Bagchi, would you please ask the next question? Please. Come on, bend. Slowly. Come on. Like this. Fine. Thank you. So my question is to the Einstein team now. Are you ready? Now you see here I have some boiling water. I have one egg. I place this egg inside this beaker. There is some tepid water here. Then I take this boiling water and put some boiling water in this, so that this egg completely submerges. Okay? Now I shall take out this egg from this hot water and place it on your hand. Okay? And you have to tell me, as time passes, how you feel on your hand, the temperature, whether you feel hot at the beginning or you feel hot a little later. Okay? I shall take it out. I take it near you. Okay. Okay. I shall take it again once more. Take it down. Take it. Do you feel the difference? So at the beginning,
It's hot,
and as the time passes,
a little cold.
is it so?
In the beginning it is cold.
Is beginning it is cold. You feel it? You feel it? Okay, give it to me. I wipe it off. I wipe the water off from the egg. I place it to your hand again.
In the beginning it is.
In the beginning it is cold.
Yeah.
And then as the time passes, when it becomes dry,
The temperature
you feel warmer. Now my question to the Einstein is, Why it is so? When you put this egg with water on the surface of this cell, you feel a little cold, then a little after you feel warm. Why? 40 seconds.
Water
26 seconds. Are you ready? Okay, fine. Who will answer? You? Okay, try.
The specific heat of water is much lower than that of the egg, and so when the egg comes in contact with the hand, the water dries up. Then we'll get more heat from the egg than we get from the water. Water has less specific heat, and so the heat content in the water is less than that of the egg.
Egg. And so when the, you said when the water dries up,
Then the egg comes in contact with the hand and we feel hot.
fine, full mark to the team. I shall try to explain. When you have this egg with water on your hand, the water evaporates and takes out heat from the cell of the egg. And when all the water has evaporated, then you feel warmer. So this is the reason. So 10 marks to the team.
No class.
Now Dr. Ghosh again.
This is a common question for both the teams. Now, we have given a candle to each team, a candle, an ordinary candle, and we have given a funnel and a pipette, and just an ordinary glass rod. Now, we will light the candles . Now, the problem is this: by making use of one or more of these things that we have given you, or without using them, you've got to blow at the candle and make the flame bend towards you. Have you understood? You have to blow at the candle and make the flame bend towards you. Now, I'll give you 1 minute to do this. Whoever does it quicker will get the credit. And you'll have to also explain.
No, don't try to. You see that pendant.
Towards you. Light it again. 41 seconds gone.
I think it's this.
52 seconds gone. No, sorry, time is up. Time is up. Give up. Now we will show you how to do it. May I have the funnel, please? Right. Now, Mr. Basu, will you please demonstrate how this is to be done? Has he been able to demonstrate? Right. So that's the way to do it, just through a funnel, and I'll explain why that happens with the help of this blackboard. Now you see, when you are blowing through this narrow tube, the pressure here is higher than the pressure outside. So when the air comes into the wider part here, it expands, and most of the air flows along the surface of the cone. And because of that, a vortex action takes place. That is, a low pressure area forms along the axis of this tube, and because of the low pressure here and the higher pressure outside, a counter current starts flowing, which bends the flame backwards inside the cone. So that is the right answer. All right, so next, nobody gets any marks.
Come. Now the next question to the Einstein team. Now you see here, in these two glasses, I have two pieces of ice, and I shall take some warm water. I am adding some warm water in this water. This water is warm now. Now kindly press this one. Now she is pressing one ice with a piece of stick. I am placing this warm water inside, and this also at the same level. So water is at the same level, this one is floating, and this one is pressed down. Now you observe which one melts first. The water is warm. The water is very hot, and the ice in both the glasses are melting, but you see the rate at which both are melting. I put a little bit. Do you observe anything? Do you observe this? Which one is melting faster?
The top one.
The one which is at the top.
One which is at the top. So, now my question to the Einstein team is, you find here that the top one is melting faster than the other one. Which one? The one that is at the bottom. My question is, why it is so? Why this one melts faster than that? 40 seconds.
There's so little pressure. There's not much pressure.
Only 1 point. Yes, we are ready.
You are ready? Please come on.
I think because the water is hot and not uniformly hot, because sufficient time was not given for the water to get uniformly hot. So when the water is poured into the glass, a convection current is set up.
In both the cases?
Yes.
In both the cases?
In both the cases.
Okay, then?
So because of this convection current, the hot water tries to go to the top, while the cold water is towards the bottom.
Okay.
So the ice piece which is floating on the top tends to melt faster than the one.
No. Would you try?
Water
No,
being
let us see.
bad conductor, it will. Water is a bad conductor. It will not conduct. It
Okay.
heats up by convection currents.
Uh-huh.
Now, when we have the ice floating, you see the water is hot. We can call it hot. Now, you know that hot water rises, cold water sinks.
So?
Now, when the ice melts, it's going to absorb some water, some heat from this hot water, and since that cold water will sink and hot water will come up,
Okay.
so it's going to melt.
Okay.
But in the second case, you see when the ice melts at the bottom, the cold water is going to stay at the bottom. It's not going to rise.
Wonderful. 5 bonus marks to the both team. 5 bonus marks to the both team. So really what they have said is like this, that when the ice is floating, then the cold water, being denser, it goes down and a convection current sets in. But in the other case, when the ice is at the bottom, the cold water remains at the bottom because it is denser, it doesn't have a chance to go up. So in this glass, the ice is always in cold water, but in the other glass, ice is always in the warm water. So it melts faster in this case where the ice is floating. So 5 bonus marks to the both team.
Now, the next question is a mathematical question concerning pigs. Now you see, we have 7 pigs. 7 pigs here, okay? Can you see the 7 pigs properly? You have 7 pigs. Now, I have given you, each team has 3 sticks. Each team has 3 sticks. These 3 sticks represent fences. They represent fences. Now, with the help of these fences, you've got to divide the whole space into 7 compartments so that each compartment has only 1 pig in it. Now, you get 40 seconds to do this. Got it? Yes, the Bose team has got it slightly earlier, but you have got it too, but unfortunately the Bose team has beaten you by a few seconds. Okay, I'll show you the answer here. You see, the answer is like this. You have the 7 pigs, and you place 1 stick like that, 1 stick like that, and another stick like that, so that you have 7 compartments and 1 pig in each compartment, right? So 10 marks to the Bose team, nothing to the Albert Einstein team. Now the next experiment by Mr. Bagchi.
Now, this question again to the Einstein team. I request one of you to come. You please come from the audience. Please come. You will help me. Now, please come here. Now you observe that I have an ear pillow, 1 ear pillow here. You see this? This is an ear pillow. And over the ear pillow, I have 1 cardboard like this. Now I shall make this student stand on that cardboard. Stand on that board. Okay? Now my question to the Einstein team is, can I blow air through this pipe into this ear pillow and make this ear pillow blow up, and then make and balance this student? Can this ear pillow blow up and balance this student? And if so, why? Can it inflate? First, no, you will be here. Can it inflate? And if it can inflate, then why? Say he has got about, say, 40 kilogram of weight. 44 kilogram of weight, okay. 40 seconds time. This is just an ear pillow. Can I inflate? First, can I inflate? Yes or no? Yes?
Yes.
Now, you have to tell me why. Let me see first whether I can. So, their answer is right, and I can inflate, and he is rising, and the pressure inside is balancing it. So, you have to answer why. How it can balance, how it can raise it.
And air act as
the pressure of the
Okay, now,
I think that,
please answer. Yes.
that when he's standing on the pillow,
Yes.
the whole weight, his whole weight
Ah.
is distributed over the surface of the
Fine.
pillow.
Yes.
So the pressure which is exerting on the air inside
Yes.
is not so great as the
great. Not great.
it's not so, it's distributed, so it's not so as high as the pressure with which we are blowing air inside the pillow.
No. Yes. The pressure which is exerted by that boy on the air pillow
Is not
is
as
less than the pressure which
with
is
which
going
we are
inside.
blowing.
Full
So
mark.
the air-
Full mark to the team. Yes. When I blow air through this tube, the air is going there under pressure. At first the air inside the air pillow was under atmospheric pressure. So when I blow air in, the pressure inside increases. Now we know that the pressure of atmosphere is 14.7 pounds per square inch. So when I increase the pressure, say it is 15 pounds per square inch. And the total area of this air pillow, say 100 square inch, 10 inch by 10 inch, 100 square inch. So total force that is acting on that board is 100 into 15. So it is about 1500 pounds total force which is acting. That means about 750 kilogram, whereas his weight is only 44. So it can balance. Fine. Now my last question is for the viewers. My last question is for the viewers. Please. No, yes, yes. Now I have here in this bottle boiling water. Now I close this mouth with a stopper, and when I put it here, you see that the boiling stops. The boiling has stopped. Now here I have ice cold water. Now I shall put ice cold water on this flask, and you see the water starts boiling. Now it is as if boiling by cooling. I put cold water and it boils. Now our experience is that when we heat, water boils, but here we find just the opposite. By cooling, the water boils. So my question to the viewers is, why it boils when it is cooled? Please send your answers to Calcutta Doordarshan. Thank you very much.